Welcome to another video. Just to make things easy for myself, because there's a lot of work and I may not have enough space, I will do all the side work on the side, but the most important things I will write on this side so I can have enough space to not erase the most important things. And that's it. If you're ready, let's get into the video. As you can see from the thumbnail and what I have here, there's some troublesome part of this integral, which is the floor of 2 times the square root of x. Okay, now this is supposed to be a rational function. This function is supposed to be something like this. Ta-da-da, like this, okay? That would be the normal rational function if this guy wasn't there. But the presence of the floor function creates a discontinuity every time x is an integer. Well, I've talked about the floor function in many cases, okay? I've done some videos in the past. But what I want you to see is that what we're going to have from this is, instead of the curve going smoothly down and continuously, it's going to be something like this. Because every time you get to an integer value of x, there's a discontinuity, a sudden drop. That's the thing about the floor function. So this integral is not just one giant integral, it's going to be the sum of many pieces, depending on how many integers we're dealing with. Well, the question says we're going from 0 to infinity, so expect some infinite series combinations. Okay. So the first thing I'm going to do is try to get rid of this guy because I cannot integrate with this guy here. So I'm going to say that from the definition of the floor function, which I've used in many floor function videos that I've done, is that if k is the floor of 2 times the square root of x, then k is less than or equal to 2 times the square root of x, and 2 times the square root of x is less than the integer after k. Remember, k is an integer, k. Okay, k is an integer. That's generally what we do. Whatever is inside the floor function will be between k and k plus 1, right? Nice. But what we want to isolate, because we're differentiating with respect to x, we're integrating with respect to x, we need to find x, okay? So let's remove the square root sign by squaring every portion of this inequality. So we have k squared is less than or equal to 4 root x, and it's less than k plus 1. Nice. So if we divide by, oh sorry, there's no more square root, I've squared it. So what we have is now k squared over 4 is less than or equal to x, and it's less than k plus 1 squared over 4. So I divided every portion by 4. Now look at what you have. If you look at the original integral, all values of x we're dealing with are between 0 and infinity. But now all values of x we're dealing with are between k squared over 4 and k plus 1 squared over 4, depending on the k you are picking. So you see why I'm saying that on that graph I drew, it depends on the region you are. So we're no longer doing one giant integration, we're doing a series of integrations that we're going to sum together. So we can rewrite this integral this way. But our value is going to be that we're starting from this lowest floor, okay? The smallest floor for any value in this thing is going to be 0. So we're going to go back and rewrite the integral as the sum of many integrals with values of k starting from 0, which is the lowest floor, to the highest floor, which is infinity. We don't know. So we're going to go here and say, let's say this is I. Okay, we're going to say I is equal to the sum of this tiny integrals, k equals 0 to infinity, of all of these integrals starting from k squared over 4, k squared over 4 to k plus 1 squared over 4 of 1 over, oh, we need to write this as dx, over x plus 1 plus the floor. But we're now writing k instead. That is the integral we're supposed to evaluate. If this explanation makes sense, we're about to keep going. Okay, now, to help us integrate well, it is better for us to do a u substitution. And because we're doing a u substitution, we're going to change the boundaries also. I'll do all the work on this side. So we can say that let u be x plus 1 plus k. That tells you that du, let's write it here, du will be the derivative of this. See, this is a constant. This is a constant. So the two of them become 0. The only thing left is this. So you got dx. Nice. So the other thing you want to work on is changing the boundaries. Okay? So if we change the boundaries for this integral, what do we get? We're going to get, if you evaluate u, when x is equal to k squared over 4, u will be equal to k squared over 4 plus 1 plus k. Well, if I multiply everything by 4 and divide by 4, this is going to be k squared plus 4 plus 4k over 4. Well, if you look closely at this, this is the same thing as, let me write it here, this is k squared plus 4k plus 4 all over 4. This is a perfect square. That's k plus 2 squared. This is k plus 2 squared over 4. So we know now that when we generate a new integral in terms of u, oh, there's a square here. Come on. So we can go here and say this is equal to the integral from k equals 0 to infinity of, the new integral would be, what's dx? Dx is du. So we can say it's basically du over u squared. But the lower limit is now this. So we can write this as k plus 2 squared over 4. Now we need to go find the upper limit. It's getting clearer and clearer, okay? So let's find the upper limit here. We're gonna get the upper limit to be, we go plug it in here. We have u will be equal to k plus 1 squared over 4 plus 1 plus k. Let me write it plus k plus 1. Okay, now the good thing I can do here is I can multiply this by 4 and divide by 4. It doesn't change anything, right? But it makes this easy because I see k plus 1 squared here. I see k plus 1 here. I can factor out k plus 1. I got k plus 1 here. And what's left is going to be k plus 1. And then I have 4 remaining. So k plus 1 plus 4 is k plus 5. K plus 5 over 4. That's what I have here as the upper limit. So I have k plus 1, k plus 5 over 4. I'll move this out. So this original integral has become this integral that's super easy to evaluate, right? Because we can integrate 1 over u squared du. It's going to be negative 1 over u. Okay? Yeah, you should. Okay. That's integral of u to the negative 2. That's another way we can write this. And if you integrate, you get u to the add 1, minus 1 over minus 1. You end up with minus 1 over u. So that's what we're going to bring in here and say this is equal to the sum of k equals 0 to infinity of negative 1 over u evaluated from k plus 2 squared over 4 to k plus 1, k plus 5 all over 4. Life is beautiful. So the next thing is to evaluate this integral using these two. And by the way, because of this minus, I can switch this, or let's see what happens. So if we plug this into this, we're going to have, I'm going to do it somewhere here so I don't need to show the work. So this means I have the sum from k equals 0 to infinity of, so let's see, if we plug this in here, look, if you plug this in here, what you're going to have is, you're just going to flip this. So it's going to be 4 over k plus 1, k plus 5. That's it. Just plug this in. So you're going to end up with a minus sign, okay? It's going to be on this side. I know it's going to be on this side. So it's going to be minus 4 over k plus 1, k plus 5. That's what you get. Now if you plug this in, the minus minus is going to cancel, so this becomes the positive one. If you plug this in, it's the same thing, it's going to flip. So this is going to be 4 over, this will be k plus 2 squared. That's it. Okay, now what do I know? I know that these two sums will converge because they are squares and they're not like harmonic series kind of series. They're not harmonic. These are squares, so they will converge. So I confidently could split it in two so that this is different from this. I want to treat this differently. So I'm going to write it, pull the 4 back and write 4 times the sum from k equals 0 to infinity. And then I have 1 over k plus 2 squared minus, here I'm going to leave the 4 on top because I have a reason. When I did it, I noticed that it was better to leave the 4 on top. So it's going to be 4 over, this is going to be k plus 1, and this is k plus 5. Nice. Am I missing anything? No. Now, let's pay attention to this guy because the next thing I'm going to write is the answer. Okay? Pay attention. Whenever you have a series, an infinite series, for example, and you don't know what it is, just start by plugging in the values. Let's plug in k equals 0. So if you look at this, this is going to be 4 times, this is k plus 2 squared. When k is 0, this is going to be 2 squared, 1 over 2 squared, plus 1 over 3 squared. When k is 4, when k is 2, this is going to be plus 1 over 4 squared, plus, tap, 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 it goes on all the way to infinity. This is part of the sum of the squares of reciprocals of natural numbers. If we only had 1 over 1 squared here, but it's missing, right? So this really is the sum. The sum from k equals 1 to infinity of 1 over k squared. This is the sum of the reciprocals of squares of natural numbers. 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared. The only thing missing is this guy. So if you know this sum naturally, which we know, this is called the Basel problem. Okay, the Basel problem is pi squared over 6. That's the sum. The only thing missing is 1 over 1 squared. What is 1 over 1 squared? It's 1. So if we subtract 1 from this, we got this. Because the only thing missing was 1 over 1 squared in this whole thing, right? So we can go back here and say that this answer I have here is equal to 4 times this, pi squared over 6 minus 1. This side is done. Let's go to the other side. So for the other side, because you're doing a sum, come on, k equals 0 to infinity. Because you're doing a sum like this, and this is a product, it's you have to split it into partial fractions. So we have to do the partial fraction decomposition for this, and you might end up with a telescoping series, and then they will cancel out, and you see what happens in the end. So let's break this down. I'll do it here also. So we know that 4 over k plus 1 times k plus 5 equals a over k plus 1 plus b over k plus 5. Okay? This is a good example of when to use the cover-up method. okay? But it looks like maybe we won't use it this time. So let's just let it be. Okay, let's not use the cover-up method. Let's just let it be. Now here, if you multiply, you get 4 equals A times K plus 5 plus B times K plus 1. Okay, you cross multiply this way and you take down the numerator. When K is negative 5, this is going to be 0, and your B is going to be negative 5 plus 1 is negative 4. Negative 4B equals 4. So that means B is minus 1. So it means we can go here and say this sum is actually the sum. You have minus 1. We said it's minus 1, right? Minus 1 over, for the B, K plus 5. And if we do the second calculation, when K equals minus 1, when K is minus 1, this is going to be 0. This would be A times 4. 4A equals 4. That means A equals 1. So A equals 1. 1 over K plus 1. So we have 1 over K plus 1. K equals 0 to infinity here. So here, if we try to plug in numbers, let's see. So here we're going to have 1 over 0 plus 1. That's 1 over 1. 1 over 1 minus 1 over 0 plus 5 minus 1 over 5. That's the first one. Then we're going to add. Okay? So this is what we usually do. And then we go to the next one. 1 over, what is it? When K is 1, this would be 1 over 2 minus 1 over 6. Tap, tap, you can easily continue. 1 over 3 minus 1 over 7. And then you have plus 1 over 4 minus 1 over 8. And then you have plus 1 over 5 minus 1 over 9. Okay? So, now something you can see is that the ones on the left are increasing, the ones on the right are also increasing in the denominator. So, this negative 1 over 5 will ultimately be taken out by this positive 1 over 5, which predicts that this negative 1 over 6 will ultimately be taken out by the next parenthesis. So all the negatives that you have here will be taken out eventually in the future by something that's positive. The only guys that will never be taken out are the initial positives before you got to 1 over 5. So this will remain, this remains, this remains, this remains, but this is gone. So we know that leftovers will include 1 over 1. We're going to have 1 over 1. We're going to have plus 1 over 2, plus 1 over 3, plus 1 over 4 from the beginning part. Now from the ending part, we don't know how it's going to end. But one thing we can predict is that the things on the right are always canceled out by the things in the future. Look at this guy on the right, needs something in the future. But the last 4 will never be canceled out because there's nothing in their future. Okay? So the last 4 are going to include stuff like this. K plus 2 plus 1 over K plus 3 plus 1 over K plus 4 plus 1 over K plus 5. These are the last 4 terms of this sequence. These are the beginning 4 terms. But remember, we're still taking the sum. But at this point, we're no longer using the sum expression. We just take the limit as K goes to infinity. Because at this point, we're almost at infinity. Okay, let me say that. So this is basically the limit as K approaches infinity of whatever you have. You're just adding. Remember, we're adding all of these sums as K goes to infinity. We started from 0. We have found the result for the earlier part, but toward the end, that's going to infinity. Remember, the constants will stay the same. These are the ones that you need to evaluate. But this is easy to evaluate because as K approaches infinity, K plus 2 will be infinity. 1 over infinity is 0. This is 0. This is 0. This is 0. So the only parts that matter are these parts. Okay. Excuse me. Okay. Now, so we can multiply this out. We're going to have 2 pi squared let's just write it as 4 pi squared over 6 minus 4 minus this limit. Okay, let's do it this way so that looks cleaner. I can just add this. So this is going to be equal to 2 pi squared over 3 minus 4 minus this limit. All of this will be 0. So if we add up all of these terms, this is just going to be, the LCM is 12, so I can say minus 12 plus 6 plus 4 plus 3 all over 12 plus, this is 0 plus 0 plus 0 plus. So each of these limits will be 0. Okay, I already stated that. So what do we get? 25 over 12. What does that look like? That looks like I have 8 pi squared over 12 minus, this is going to be 73 over 12. Nice. So I think this is it. Okay, and we can actually combine the top and just leave it that way. So we can say it is 8 pi squared minus 73 over 12. This is the value of this definite integral. It's been crazy, but I'm glad I left as much information on the board for those who want to look at them. Never stop learning. Those who stop learning, stop living. Bye-bye.